So in the last segment, we talked about reductions, and I pointed out the following nice implication of reductions. If problem A reduces to problem B, and problem A is known to be hard, then B is also hard to solve in polynomial time. Hard here means not solvable in polynomial time. Another way of saying it is if A reduces to B, then B is at least as hard as A. So think about that for a minute. So a reduction shows you that if one problem reduces to the other, the second problem is at least as hard as the first problem. So this will allow us to talk about the hardest problems in NP, which was our goal when we defined reductions. Suppose we have a decision problem A in NP, and we can show somehow, and this seems almost impossible to imagine how at the moment. Suppose we have a problem A in NP, and we can show that every problem in NP can be reduced in polynomial time to A. What does that mean? That just means that A is at least as hard as any problem in NP. Because if we knew that A is solvable in polynomial time, then every problem in NP can be solved in polynomial time because of the pipeline using the reductions that we saw a couple of times in the last segment. So meaning if A is in P, if A is solvable in polynomial time, then P equal to NP. So coming up with a polynomial time for A, polynomial time algorithm for A is basically showing P equal to NP. So A could be called the hardest problem in NP. So now we are able to define a hardest problem. And we're going to call these hardest problems, and there'll be many of them, not just one problem that's the hardest problem in NP, but a whole bunch of problems that are going to be called, they're going to turn out to be the hardest problems in NP. And what defines the hardest problems in NP? These problems are going to be called NP complete. A problem is NP complete, A is NP complete if A is an NP, and every problem in NP reduces to A in polynomial time, of course. We always talk about reductions in polynomial time. So in polynomial time, polytime. Remember that we're always talking about decision problems for these segments. So A is a decision problem. So a decision problem is NP complete if it's an NP and every problem in NP reduces to it. Intuitively, it means that A is the hardest problem in NP. How do we show that every problem in NP reduces to a problem A? This is challenging because there are an infinite number of problems in NP. How do we show that every one of them reduces to one particular problem? That's not at all obvious. In fact, it took two great computer scientists, logicians, to prove the first problem that was NP complete. And this is the famous Cook-Levin theorem. And Cook and Levin proved that the problem of satisfiability is NP complete. And I won't be able to talk about their proof, but I'll at least explain to you what the satisfiability problem is and how we can use the fact that it's NP complete to show that other problems are as hard as satisfiability. So what is satisfiability? So the problem is, given a Boolean formula, and I should explain what that is there a way to set the variables such that the formula evaluates to true? That's the satisfiability problem. What's a Boolean formula? To talk about that, we first need to talk about Boolean variables. These are variables like x and y, which only take the values 0 and 1. So they can either be 0 or 1. 0 you should think of as false, and 1 as true. So you can think of it also as being as sort of variables that take on the value false and true. Now, in a formula, these variables can be combined by different operations. So one operation is to take the not of x. Not of x is has the opposite value of x. So if x is true, not of x is false, and if x is false, not of x is true. So that's denoted like that. You can take two Boolean variables and take their OR, denoted like this, x or y. And x or y is true exactly when at least one of x and y is true. Either x is true or y is true or both are true. In this case, x or y is true. And finally, you can combine two Boolean variables and write x and y. And this is true if both x and y are true. So these are intuitive sort of English concepts, and or. There's a slight difference about or. X or Y is true even if both X and Y are true. So X or Y is true either if one is true or both are true. So that's the basic operations in Boolean algebra. You have Boolean variables and you can connect them with ors and ands and nots. And a formula is just a long expression that's formed up of Boolean variables in these connections. So here is an example. Not A or not B or C, and A or C, and not C or B, or not A or B and C. So this is a formula. It's a complicated formula. And you can see that it's satisfied with the following assignment. What does it mean by satisfied? It's basically if you plug in the values for these variables, you give A the value 1, B the value 0, and C the value 0, and you plug them in here, the whole formula should evaluate to true. In that case, we say that this assignment of values, this assignment here, is a satisfying assignment. This is a satisfying assignment of values to the variables. So let's check for ourselves that this is a satisfying assignment. If you give A the value 1, what happens to not A? Well, that becomes 0. Not A is the opposite of A. Not B, well, B has the value 0, so not B has the value 1. C has the value 0, so this is just 0. 0 or 1 or 0 is 1. The OR is 1 whenever any one of the variables is 1. So this part gives the value 1. A or C. Now A is 1. C is 0. So A or C is also 1. So this part also has the value 1. And then this part has the value, not C is 1, B is 0, so this part also has the value 1. Now you're taking the AND of these three parts. They all are 1, and AND is 1 whenever all the parts are 1. So these three parts are all 1, so their AND also gives us 1. And finally you have this part here, which is 0, 0, 0. So this part is 0. So this whole first part is giving us the value 1, and the second part is giving us the value 0. We're taking an OR of those two things, and that has overall has value 1. So everything together has value 1. So this is indeed a satisfying assignment to this formula. So I hope you understand what a satisfying assignment is and what a Boolean formula is. There's a lot of references you can find explaining Boolean formulas and combinations and so on in greater detail. So the Cook and Levin theorem says that the problem of determining whether a Boolean formula is satisfiable, note that that's a decision problem, because given a Boolean formula, either it's satisfiable or not. So it's a decision problem. And the problem of deciding whether a Boolean formula is satisfiable is NP complete, meaning it's the hardest problem in NP. Well, why? So at least one part of it is easy. So given a Boolean formula, suppose it is satisfiable, what would be a solution that would convince you that that Boolean formula is satisfiable? Well, if someone told you, try this assignment, make the first variable 1, make the second variable 0, or whatever, try this assignment and check that the formula is satisfiable for that assignment. If someone gave you an assignment to the variables, it's easy for you to check that if you plug it in, you get the formula evaluating to 1. So that's why verifying a solution is in polynomial time. Therefore, this problem is in NP. How to prove it's NP complete, I won't go into, but basically Cook and Levin said, take any problem in NP, look at how a verifier for that problem would work, and show how you can convert it to a formula that is satisfiable if and only if the input to the original problem is in the language. So don't worry about that last part. Cook-Levin theorem is not part of this course. But assume that we've proven that satisfiability is NP complete. One other thing to note about reductions before we use this knowledge is the fact that reductions are transitive, meaning that if you have three problems, and we can reduce A to B and we can reduce B to C, then you can also reduce A to C. So this picture says it all. You can chain reductions together and get a reduction from the first problem to the third problem if you have three problems. Bear in mind the reductions are transitive, and now let's see what we can do. So once Cook and Levin showed that satisfiability is NP complete, what does that mean? They show that satisfiability is in NP, and every problem in NP reduces in polynomial time to satisfiability. Now, to show a new problem X NP complete, our task is a lot simpler. We just have to show that X is in NP, and then show that satisfiability itself reduces to X. And that's all. Because if you show satisfiability reduces to X, then see what happens for any other problem A in NP. So if you have problem A in NP, by the Cook-Levin theorem, we already know that it reduces to satisfiability. Let me write it as SAT. And now if you show that SAT reduces to X, then you've shown that any problem A reduces to X by this transitivity. So all you need to do once you have Cook-Levin is that show that SAT reduces to this problem X and show that X is an NP. Then you would have shown that X is one of the hardest problems in NP. It's an NP complete problem. Just as an example of a reduction, a toy example just to get you started, let's consider the problem of non-unique satisfiability. So determine whether or not a given Boolean formula phi has at least two distinct assignments that satisfy it. So meaning not just one assignment of values to the variables, but two different assignments of values to the variables that both cause the formula to evaluate to true. That's the non-unique satisfiability problem. Let's call it NUS. NUS is in NP because how would someone convince you that a particular formula is a yes example of NUS? Well, they would present a solution which consists of two different assignments that satisfy the formula. And the verifier, the polynomial term algorithm, that's U, can just plug in each of the assignments and check that each one satisfies the formula phi. So NUS is an NP. Now how do you show that NUS is NP complete? You can reduce satisfiability to NUS. Given an input phi for satisfiability, we create a new input for NUS, which is a formula psi, which is phi and a new variable x. This has not been used in phi at all. It's a completely new variable x. And we write down and x or not x. Now notice the following things. If phi is satisfiable, the original formula input to satisfiability is satisfiable, then you could actually find two assignments that satisfy psi. Because you could take the assignment that satisfies phi and choose either x equal to 0 or x equal to 1, both of which would satisfy the whole formula. So basically, this is the original assignment satisfies phi concatenated with the assignment of 0 to x, or the original assignment that satisfies phi concatenated with the assignment of 1 to x, both of which satisfy psi. So if phi is satisfiable, psi has two distinct satisfying assignments. In other words, if phi is a yes input for satisfiability, psi is a yes input for NUS. On the other hand, if psi has two distinct solutions, is non-unique satisfiable, it has two distinct satisfying assignments, then we can check that the original formula phi must have a satisfying assignment because this part must also be satisfied by either of the satisfying assignments, and that's any assignment satisfies phi is a satisfying assignment for the original formula. So you can see the reduction goes both ways, meaning if the input is a yes example of satisfiability, it maps to a yes example of NUS. If the input is a no example of satisfiability, it maps to a no example of NUS. So therefore, this function phi, and this function f that maps phi to phi and x or not x, is a polynomial time reduction from satisfiability to NUS. And this proves that NUS is NP complete. Okay, this is something you should think about a little longer because this is a very trivial example, but at least you should understand the mechanism of reductions from this example. And next segment, we will see a little more sophisticated example of reductions.